It'll separate into N2 and H2. And then if I just direct the hydrogen into a small area...
To boldly go where no one has gone before.
That's one small step for man, one giant leap for mankind.
Space, the final frontier. Its horizons, from our limited human perspective, stretch out over a practically infinite distance, which itself is only a small fraction of what lies beyond. It has captured our imaginations and laid the foundations of the hopes and dreams of many. We long to reach out and touch the stars, despite their immense separation in distance and in time. I still vividly remember the night when my dad and I went out to stargaze for the first time, and although the sky was partially clouded by a pestering bright hue from a nearby Virginian city, he still managed to point out that dim pinprick of red light in the sky that represented the enigmatic planet where alien invaders always seem to come from, Mars. But that wouldn't be the last time my old man would take me out to see the stars. Jupiter, Sirius, Rigel, Betelgeuse, plus a friendly, digestible explanation of the speed of light itself. But one object, or I suppose series of objects, that stood out to me then as well as now, is this little strand of starlight in the constellation of Orion the Hunter. This trio of stars is known as Orion's Belt, named so because they appear to form around Orion's would-be waist and hold the sheath to his sword. I don't remember exactly where it came from, but as a kid, I was totally fascinated by Orion's Belt. After all, three bright stars right next to each other in such perfect order, it seemed so pristine. I could only imagine how attractive and convenient this formation could be to anything able to lay eyes, or anything akin to eyes, on it. I remember many nights spent where I would stare at these stars for hours, thinking about the grand fleets of trading ships and all the scientific and patrol vessels of unearthly design that must have at that very moment been passing through a sort of Orion highway, all hailing from parts of the Milky Way unknown, their destination lying at some other part of it, many, many light years from home. Perhaps some of them may be making pit stops to repair or refuel around the magnificent and beautiful planets that must surely orbit these equally magnificent and beautiful junction stars. A whole medley of fascinating, intelligent beings sharing stories and knowledge of our galaxy with one another. How I wished so badly I could be with them for even a single Earth day, and how much I would have loved for humanity to join them. But, unfortunate as it may be to my young self, this highway of Orion is likely not to be. Science fiction, eventually, must give way to science fact. Meet Alnitak, Alnilam, and Mintaka, the three principal stars of the belt. And although Alnitak and Mintaka are both at comparably similar distances from the Earth, about 1,200 light-years and 1,300 light-years respectively, Alnilam is almost double that distance at over 2,000 light-years. Yet, despite being so far away, it also appears to be the brightest of the trio. This is because Alnilam is a blue supergiant, over 60 times as massive as our Sun, and over 800,000 times more luminous. Interestingly enough, this would also likely make the role of Alnilam more important in the formation of astronomical culture to any developing alien civilizations in or around Orion's belt than it was to any here on Earth. To any Alnitakians or Mintakans, Alnilam would play a role comparable to our very own Sirius, Alpha Centauri, or Arcturus. This is, of course, at the cost of never knowing they were part of the most wondrous and mysterious groups of stars, likely able to be seen lingering next to one another from all sorts of angles and orientations within our local stellar neighborhood. In a way, though, such thinking is even more uplifting than what younger me envisioned. While the Orion constellation may not be a hustling cosmic interstate voyage by space truckers, it is still A region of space overflowing with stars, and orbiting around every star is a chance for life. Someday maybe, we'll manage to pave ourselves a road through space, and just maybe, that road will intersect with another, and form for real those junction stars that must surely exist somehow and somewhen. But what would such a journey even look like? Where would it take you? And where would we even want to go? Before we can ask where and how, we must first ask why. Why travel to space? Why spend money on going back to the moon? Why send an expedition to Mars or drones to Titan? Most people this generation will likely never even see low Earth orbit, much less the surface of another world for themselves. So, what exactly is worthwhile about putting another small group of people on another world? Of course, the most abstract answer to this question probably has something to do with the indomitable human spirit. We can, therefore we should, beckoning adventure and all other manner of romantic ideals. But romanticism is a rough thing to buy the hardworking taxpayer with, and just because you can does not automatically mean that you should. For our fledgling generation in particular, there needs to be some kind of incentive, and for better or for worse, we're lucky in that regard. Spreading out across space and diversifying our habitats is, in a way, the perfect insurance policy. If something were to happen to Earth, say a large, unstoppable meteorite impact, or, heavens forbid, a life-cleansing nuclear war, humans on the moon or Mars or an outer solar system moon would be left unscathed. There's also an economic boom to be had. Helium-3 for rocket fuel on the moon, metals in the asteroid belt, the ingredients for synthesizing plastics on Titan, untapped global reservoirs of water and ice on Europa and Enceladus, and naturally, the most precious commodity of all, living space for untold future generations of people. It may sound almost science fiction, but these are all things that humanity is teetering on the verge of really realizing. Artemis 3 is set to land humans on the moon once again in 2026, with China not far behind. Their Chang'e program is set to land humans on the moon as early as 2029, and the ultimate goal of both of these programs is truly remarkable: the establishment of permanent lunar bases to facilitate manned missions to Mars and beyond by 2039. Within our lifetimes, we are finally set to become an interplanetary species. I hope so immensely that we don't manage to lose track of these goals when we are so close to reaching this once impossible dream of an untold number of human beings before us. But not everyone is a pioneer or proverbial gold miner. Some people may just prefer to sit back at home with the morning brew in one hand, the Earth's 9.81 meters per second acceleration beneath them, and scientific publication in the other hand. Why go out and mine that rumored to exist asteroid made of solid silver or platinum when you can learn all about it from home instead? If you're not sold on the material value of such endeavors, then the science and vast pool of knowledge behind them might be able to hook you. Take our neighboring celestial body, the moon. A scientific presence on the moon goes beyond just examining dust and rocks or even just mining new sources of helium. The moon is a haven for advances in various sciences, the most tantalizing of them residing in astronomy. This is the proposed NASA Lunar Crater Radio Telescope, designed to be over 3 kilometers wide, with the main antenna itself being about 1 kilometer wide. It'd be the largest telescope ever built by mankind, and it would float suspended above one of the deep craters on the far side of the moon, safe from passing satellites, a reflective ionosphere, and pesky ground-based transmissions. Such a telescope would allow us to peer into and study the universe's early history with unprecedented detail and precision. But even if we never built such a structure, the idea of building observatory-standard telescopes on the moon can be traced back in their origin to the Cold War. Practically unimpeded from a clear view into space, lunar observatories would allow us to study in greater detail distant stars, exoplanets, galaxies, and from the moon, journeying in large vessels assembled in lunar orbit, we would walk, for the first time on another planet with Mars. Inspect close up the likely habitable subterranean ocean of Europa. Construct dams for hydroelectricity in Titan's flowing rivers. Hike the icy mountain ranges of Pluto. And centuries from now, when we've thoroughly explored our solar system, we will once again debate why, and venture off into that vast and open Milky Sea. Interstellar space, though often described as such, is hardly a void. Within galaxies, stars are packed together so densely that there could be dozens or even hundreds of them across a length as short as 10 light-years. As opposed to the wooden ships of the past, spacefarers, I imagine, will find it hard to become lost in the cosmic ocean. In that sense, maybe space travel will be a quasi-mix between an ocean voyage and a road trip. Without a doubt, the spaceships of the future will rely on computer-set courses to navigate the space between stars. But if all else failed, or the want for a challenge took over, maybe onboard navigators would plot a course based on the orientation of our galactic center, and a nearby grouping of stars, or a nebula in their viewport. Their course also aided by the patterned radio signals of known pulsars. Imagine that. An interstellar voyage that could be planned or salvaged with a pencil and paper, a properly tuned radio receiver, and an understanding of our galaxy's landmarks. It'll be somewhat reminiscent of the drives we take in cars today. The pilots of these spacecraft as undaunted as we are enjoying time out with our friends. Charts, courses, and reasons are all well and good for making talk, but talking itself doesn't actually make anything happen. We need action for that, and design ourselves a spacecraft. One which will reliably transport humans to other worlds. But what exactly would that word reliably even mean in the context of such an endeavor? I would guess it has something to do with achieving a specific outcome. For some, reliable just might mean advancing our knowledge of the cosmos over a slow, steady course of several thousand years. For others, it could mean forging a galactic empire of science fantasy proportions over the course of several dozen years, plus anything in between. Some wanted outcomes could be achieved with technology we already have or will have in the coming decades. Some would require unprecedented, even improbable breakthroughs across our understanding of physics and chemistry. Before we can discuss the methods for how future humans may colonize space, we need to talk about how they likely won't.
Somewhere in space, this may all be happening right now. 20th Century Fox and George Lucas, the man who brought you American Graffiti, now bring you an adventure unlike anything on your planet. Star Wars.
Here they come.
Star Wars, the gateway sci-fi for many geeks, including myself. I still very vividly remember my first time watching A New Hope at age 5. I remember I used to call Han Solo Captain of the Millennium Falcon - Rendar, because my actual first exposure to the series was the Shadows of the Empire for Nintendo 64. And Harrison Ford seemed to resemble Dash very closely. I also very vividly remember seeing a hyperspace jump for the first time. It very well might have been the first time I had ever encountered the concept of faster-than-light travel. Though Star Wars did not create the concept of hyperspace, subspace, jump space travel, whatever you want to call it, it is the most popular series to utilize it. Hyperspace is essentially a dimension of our same universe, higher up from the third dimension in which we normally reside. This higher dimension essentially functions as a substantial contraction of three-dimensional spacetime, like a sheet of paper being crumpled into a wad that allows for travelers to cross universal distances in exceedingly quick times, even without traveling close to the speed of light. When they pop back into the third dimension, they remain in the same corresponding position as in hyperspace. As interesting as it may sound, it is also very likely a total work of fiction. As far as Einstein's relativity is concerned, a higher space-time crumpling dimension is incompatible with our understanding of physics, and even if it did exist, it's very likely impossible to ever cross into. However, there is one mode of fast travel across cosmic distances that may turn out to be quite real, a method by which you could cross from our solar system into a galaxy many millions of light years away, the traversable wormhole. Although they have never been confirmed to exist in the natural world, they're still very mathematically sound, a byproduct of Einstein's field equations. Even though one has never been thought to be observed, it wouldn't be too shocking if we eventually happened upon one. After all, we didn't identify the first black hole until the 1970s, and they were also something mathematically demonstrated by Einstein. It's far from impossible that wormholes are out there somewhere, and we just don't know how to recognize them yet. A traversable wormhole essentially functions as a bridge between two corresponding points in space. Whereas two locations in the universe would normally need to be traveled between, a wormhole essentially pinches a pair of points in spacetime substantially closer together, allowing for quicker or even instantaneous travel between them. But, assuming they exist in the first place, there are problems that would need to be addressed before you could go ahead and plunge your way down into one. The biggest problem being that wormholes are very unstable things. If we wanted to traverse a wormhole reliably and safely, without it closing on us before we finished our journey, we could stabilize it and keep it forced open with forms of exotic matter, exerting powerful outward gravitational forces. But exotic matter itself is also unknown to exist, and comes with its own set of unique paradoxical challenges. Ultimately, it seems like too much work. Even if wormholes exist, until they can be stabilized or otherwise made deemed safe to travel, it's probably best to avoid them. And we would still need the ships to carry us to them anyway. It might just be more efficient and less of a headache to focus on new, man-made methods of transportation. One engine of spacecraft propulsion you may have read about in the news at some point in the past few years is that of the Alcubierre Drive, named after Mexican theoretical physicist Miguel Alcubierre, although you may know it as the warp drive. Popularized by the sci-fi series Star Trek, a warp drive, as opposed to a hyperdrive, is based on real physics. In the case of the Alcubierre Drive, inspiration is taken straight from relativity, and it would allow for faster-than-light travel. Under normal circumstances, any object with mass cannot travel at or faster than light. But a ship equipped with this very not normal engine would do something very unusual. It would contrast the space ahead of it and expand the space behind it, warping around it a bubble of spacetime that would be pushed and pulled along. The ship itself would not be accelerating through space, rather surfing along the dimensions of space itself. And because the ever-expanding fabric of space-time is not subject to obeying the speed of light, our ship is limited in travel speed only by how strong of a warping effect it can cause. Principally, such a ship could allow for travel speeds upwards of 10 times the speed of light, or 3 million kilometers a second. It sounds like such a tantalizing prospect. This method of space travel would present an opportunity for real to create the sort of interconnected, lubricated spacefaring civilizations you see in media. So if we have the math figured out, why not build one right now? What is stopping us from constructing our very own USS Enterprise? Well, in order to warp spacetime so reliably and regularly, it would require the persistent generation of dense amounts of negative mass energy around our ship's hull, something that, on a macroscopic scale, remains impossible. Its generation would also likely have to be fueled by some kind of exotic negative mass matter that may not even exist. And even if you could somehow synthesize this mysterious antimatter, the energy demand for powering an Alcubierre drive might be so steep that just one of them would require an amount of fuel in the order between an entire Earth's worth and an entire universe's worth. There are also smaller issues that would need solving, such as the warp bubble being unsteerable due to the ship being causally disconnected from the front of the field, the ship's crew being fried due to Hawking radiation, and worst of all, the potential to devastate the very destination you're attempting to travel to with ultra-lethal gamma-ray bursts. Ultimately, if they are possible to create to begin with, and many physicists doubt they are, warp drives are a technology that is centuries in the future, if not thousands of years. For near-future humans, obtaining reasonable sublight speeds remains our primary vision, while faster than light travel remains just a twinkle in the eye for any would-be cosmic adventurers. But what even is light speed to begin with, and why is going at it or past it seen as a scientific holy grail? The speed of light, about 300,000 kilometers a second, is the fastest speed at which information in the universe travels. Information meaning things like gravity, electromagnetic radiation, which crucially includes the visible light spectrum, and it functions as our universe's speed limit. There are some who might find such information annoying. Why should scientists be allowed to put seemingly arbitrary laws in textbooks as if they were true? What is stopping me from going 300,001 kilometers a second aside from the demand that I can't? Once again, we return to Einstein's relativity. Let's say, for example, I was driving towards an intersection along a busy road. You would think, in a universe with no laws governing speed, that the image of my car made of reflected light should be rushing ahead at the speed of light plus my car's additional velocity, 300,000 kilometers a second plus 80 kilometers an hour, as I'm about to cross. And if you, driving recklessly, were approaching from my right side of the intersection at 160 kilometers an hour plus the speed of light, your image ought to arrive at the intersection that much faster than mine. From my perspective, I would see an imminent car crash and swerve to avoid being hit. But from your perspective, it would look like I just took a sudden sharp turn off the road for no reason at all. In reality, no such thing ever happens. As anyone who's ever been in a car crash can tell you, there's never a paradoxical delay between the image and the impact. There's only ever a sudden contact between all the vehicles involved, all at the same time. As Einstein pointed out, for the universe to remain logically consistent, and for us to avoid life-altering paradoxes, then there are rules that must exist that govern the transfer of information. Chief among them, that the speed of light is a universal constant, remaining the exact same whether being transmitted from an object at rest or an object in motion. No further velocity under any circumstances can be added to it. In addition, no object with any mass of any kind, not even the subatomic particles contained inside an atom, has the ability to travel at the speed of light, although in principle, there is nothing stopping any object with mass from traveling as close to the speed of light as desired. 25% the speed of light, 75%, 99.99 repeating percent, all of them are equally permissible, but 100% will always remain unreachable. 300,000 kilometers a second, the constant speed limit of our universe. But it gets stranger than that. The physical, three-dimensional form of the universe is interwoven with an omnipresent, additional invisible fourth axis, the dimension of time. Collectively, this intricate weave is referred to as the fabric of space-time. To accelerate through one is to accelerate through the other, and always while following the light speed limit, something the universe makes sure to strictly enforce. And as such, very strange things happen when approaching the speed of light. Suppose you woke up early one morning to find a family member or best friend had gifted you a spaceship, one that could travel at 99% the speed of light. You're excited to test it out, but know you have something important to do the next day. So instead of doing something time-consuming like traveling to a nearby star system, you instead go with a modest first joyride to your favorite dwarf planet Pluto, a mere 5.5 light hours away. As you take off from Earth orbit and begin to accelerate through open space, you would see something strange begin to happen outside your ship's windshield as you approached in near-light speeds. The stars within your field of view would appear to contract further and further into a single point within the center of your vision. You would also begin to see the light coming from behind your field warped around the edge of what's in front of you, a result of partially catching up to the photons traveling away from objects behind you. The center of this field would also, due to the Doppler effect, become increasingly brighter and blue-shifted, while the edges became increasingly dimmer and red-shifted. Closer you approached the speed of light, the more and more contracted the light would become, until your entire visible universe would appear in front of the ship, while behind you there appeared to reside an eerie void of nothing, until you decided it was time to decelerate so you wouldn't accidentally overshoot your destination. You park into Pluto's orbit, and you take a few still hours to ogle at the grand Plutonian sights. Maybe you even spot Karen, hanging in the sky nearby, a view that's surely worth an interstate drive's worth of time. And of course, you repeat this process over on your way out of the Plutonian system. When you arrived back at Earth, any clocks on the ship would confirm that from your perspective, you've been gone for less than a full day. But from the perspective of the Earth, you've been gone for many years. The world you've returned to has become very different from the one you departed from, and your family and friends have already for so long moved on with their lives and passed away. You have now very thoroughly experienced the phenomena of time dilation. It may seem hard to believe, but time dilation really is something that happens. Clocks on jet planes will run slower than stationary clocks. GPS satellites take it into account, so they always provide reliable routes. And massless photons traveling at light speed decay far slower than particles of mass traveling at near light speed. Time dilation is a foundational law and essential function of the universe. Einstein redefined our understanding of physics with his laws tightly encased within general and special relativity, but he himself didn't live long enough to see the stunning achievements of the space age, defined by and designed around his discoveries. The mapping of Mars with the Mariner program, the hellish landscape of Venus with the Venera missions, the cold, dim surface of Titan with the Cassini-Huygens probe. And now, in the current day, we have the early stage designs of spacecraft that could one day be used to carry mankind throughout the galaxy. Despite the differences in project names, one thing all these designs have in common: nuclear power. For decades now, nuclear fission-powered rockets have been persistently sighted in NASA's crosshairs. But due to budget cuts, something NASA is particularly vulnerable to, it's never something that's been fully realized before. Project Prometheus, established in 2003, was their last major foray with fission engines. Under it, the proposed GEMO mission would have been the first of its kind, powered in part by a small fission reactor. It would have studied up close all of Jupiter's large Galilean moons. There was even a proposed European lander that would have been transported with the ship and dropped down to directly study the moon's surface, possibly, as a result, detecting signs of frozen organic matter on its surface. If the mission had been funded, parts of the craft would have been launched into Earth orbit in 2015, where the ship would have been assembled and parked to fly on out to Jupiter around early 2016. It would have entered into Jupiter's orbit in 2021, meaning now in 2024, it would have long since granted us access to great collections of data and up-close looks at the Jovian moons unlike any other, with still at least another year of mission duration. But in 2005, the project had its funding pooled, and the staff were reassigned to other things, thus sealing the ambitious GEMO's fate. Decades before that, you had the tragic NERVA program, case that makes space exploration nerds the world over shed a tear. Under this program, while the space race was in full swing, several nuclear reactors built explicitly for spaceflight were successfully built and extensively tested throughout the 1960s. At the peak of NERVA's testing, there were real plans drawn up for using nuclear-powered rockets that would facilitate a manned mission to Mars by 1980, the establishment of permanent lunar bases by 1985, and several permanently manned space stations shared between Earth and the Moon. But the political will was very mismanaged. The Apollo program was already eating up much of NASA's budget, and the already raging Vietnam War, which the US would go on to eventually lose, began to sway Congress's focus away from space travel. And by 1970, NERVA was deemed an unnecessary expenditure. It would finally be terminated by President Nixon in 1973. Though the project had its share of development issues like any involving spaceflight, the vision was there. What was lost and what might have been, well, who can say? However, all is not lost. With the 2020s came Project Draco. With this initiative, in conjunction with DARPA, NASA plans to have working fission-powered spacecraft engines developed and ready for demonstration by late 2027, provided they keep their funding intact. They'll subsequently be used to carry crucial material to the moon to aid with the establishment of permanent human presence, until years later, when those same engines will help carry mankind to Mars. The importance of nuclear-powered spacecraft cannot be understated. They would greatly reduce the travel times of manned missions between Earth and Mars significantly, from 7 months to 1.5. Pluto, at the edge of our solar system, could be reached by a manned mission in less than 5 years. Of course, another great thing about nuclear engines is the allowance for the construction of spacecraft with more mass to them. If you were to pair that allowed increased mass with low-gravity base lunar construction rather than high-gravity Earth-based construction, the mind just races with possibilities of what a wondrous age of spacecraft design we're about to happen upon. A 100 years from now, there may be designs for advanced survey ships to transport scientists to the outer solar system. Freighters 100 meters long being assembled in space, with refined asteroid belt material, perhaps. Passenger liners to transport Earth workers and immigrants to lunar and Martian colonies. Small, powerful probes being sent to get our first views of various Kuiper Belt objects. An idealistic vision, perhaps, but one that could be achieved if we really make the effort. As lovely as the upcoming generations of fission spaceships sound, it could be possible that they may not reign supreme for too long. In recent years, massive strides have been made in the world of nuclear fusion, a much more reliable and efficient form of nuclear power, but also one that has remained outside the practical reach of human technology. It has only been in the last couple years that fusion reactors have become efficient enough to put out more energy than what's put into them. So this type of craft remains a frontier in engineering in need of further exploration. This prospect is something that has been fantasized about for many decades now. In the 1970s, the British Interplanetary Society laid out a design for such a spacecraft, named Project Daedalus. This unmanned ship design backs upon the existence of a powerful enough onboard ICF, or inertial confinement fusion drive. The Daedalus probe would carry enough propellant to reach around 12% the speed of light after about 2 years of acceleration, meaning Alpha Centauri 4 light-years away would be reached in less than 4 decades, not even half a human lifetime. It sounds science fiction, and it may be for now, but according to many physicists, fusion, as well as fission-powered engines, could someday really be used to accelerate manned and unmanned missions alike to speeds between 10 to 40% the speed of light. A comfortable range where interstellar travel times become practical and the effects of time dilation can largely be ignored. Both for the near future and the far future, I have no doubt these methods of propulsion will be the modus operandi for a steadily expanding human race. If we don't destroy ourselves, if we stay true to the course, I expect the ships our distant grandchildren use to carry themselves to neighboring stars will foundationally be little different from the ships we will use to carry ourselves throughout the solar system. And with those future prospects, there also comes the guarantee that this technology will improve and become more refined over time. Could it be possible that we may one day use these ships to explore all the Milky Way? And what about the possibility of leaving the Milky Way altogether? Could we use nuclear power to one day visit another corner of the universe? Imagine if you were a starry-eyed space adventurer living on an Earth, not 1 or 100, but 1,000 years from today, when the power and size of spacecraft has become unimaginably greater in scale than anything we have in the 21st century, and that one of these ships was yours to helm. It comes with its own labs capable of growing food and synthesizing water, and your ship's reactor is so sophisticated it can last for hundreds of years at full power without needing to refuel. Let's also say this awesome top-of-the-line vessel of the 31st century had engines powerful enough to constantly accelerate at 1 G, with brakes being only briefly taken to keep you and your crew from being squashed by immense g-forces. After maybe 2 years had passed on the ship, we would be at 0.99 c, 99% the speed of light, with the decimal points continuing to compound, and time continuing to slow more and more by tremendous factors. But by what measure? The Vega system, 25 light-years away, could be reached in about 10 years relative to you. The center of our galaxy, 27,000 light-years away, would be reached in about 20 years. The Andromeda Galaxy, over 2 million light-years away, in about 30. But even more eerie, in theory, a trip to the edge of our current observable universe, 46.5 billion light-years away and back again, could be achieved in under a single century. But the people back home wouldn't see it that way. You would find yourself returning home over 100 billion years in the remote future, to find an aging elliptical galaxy residing where the Milky Way once stood, the Earth vaporized from existence, our species extinct, and our sun a slowly dying white dwarf. Relativistic speeds are a cosmic deal with the devil. They allow you to explore great swaths of the cosmos and provide the opportunity to see and know more than any human ever has, but at the cost of everything and everyone you know that stays behind. As stated earlier, to accelerate through space is to accelerate through time. It also wouldn't do much good. Sure, you and your crew have no doubt seen all sorts of wonderful sights and uncovered an untold number of mysteries, but who'd remain to hear about your discoveries when all was said and done? The hard truth to swallow is that space travel will likely always be a generational effort. Our generation will be the one to colonize Mars, and maybe if we're lucky, we'll get to experience a manned mission as far out as Jupiter. In the 22nd century, there might be the first attempt to colonize Titan. A century from that, the first manned outposts on Eris. And only then, another century out, will humans cross through the heliosphere, standing on our shoulders. I suppose it can be easy to feel envious in a way. Here we are still stuck on crummy old Earth, while our descendants are plying the space between stars, enjoying company with talks of exotic night skies, and time spent on worlds that remain only in our dreams. But really, I expect they'll be equally as envious of us. You don't have to be out in space to appreciate its beauty and its mystery, and a spacecraft doesn't need to have a fusion reactor or a warp drive on it to make an impact on people's lives. My favorite space mission of all time, the grand tour of the Voyager probes. It'll be considered primitive by the standards of future humans, but Voyager gave me, when I was younger, my first look at Neptune, the volcanoes of Io, and the patchwork terrain of Miranda. Voyager also put into perspective for me, and many others, how precious our home planet really is. Something humans born on Mars, or whatever they decide to name Proxima Centauri B, won't fully realize. Our culture, our appearances, our languages, originated here, and nowhere else in the universe. I suppose that's why, in the event that any other intelligent form of life, or even future humans who've forgotten all about the Earth ever found them, records containing examples of what humanity has to offer were sent into space along with the Voyagers.
Hello from the children of planet Earth.
And until they are found and examined, they will continue to make their way across the cosmos for maybe a quintillion years. A quintillion years is a long time. Within that frame of time, Saturn's rings will have dissipated. The Andromeda Galaxy will have fully merged with the Milky Way. The inner solar system will have been totally engulfed and reduced to a scattering of atoms by the sun. The universe's expansion will have pushed every galaxy in space so far apart that no two galaxies will ever be visible to each other ever again, and the galaxies themselves will begin to grow dark as star formation ends. And through all that time, far away from home, separated by immense distances of space and time, the Voyagers will continue to fly, hitched on their backs to the echoes of a world and a species long gone. Maybe you were born too early to explore space, but you were born just in time to see galaxies in our night sky, to enjoy a misty sunrise, to see a ringed planet through a telescope, and to appreciate the people you love who don't exist in any other time. So use this time you have to know them, to know yourself, to cherish this unique world, and to prove to the cosmos that we were here.